Welcome. In this lesson, we will introduce the convolution of two functions and also use the convolution to determine an inverse Laplace transform. Recall the Laplace transform of a product is not equal to the product of the Laplace transforms. However, all hope is not lost. We simply have to use a different type of product. Take two functions f of t and g of t, defined for t greater than or equal to 0, and define the convolution of f of t and g of t as shown below. On the left, we have the notation used for the convolution of f of t and g of t. It can be written either of these two ways using the asterisk. And the convolution of f of t and g of t is equal to the integral from 0 to t of f of tau times g of the quantity t minus tau d tau. As we can see, the convolution of two functions of t is another function of t because the limits of integration are from 0 to t. And the convolution has the following properties. Notice the first property resembles the commutative property, the second property resembles the associative property, and the third property resembles the distributive property. Before we see how we will use the convolution to determine an inverse Laplace transform, let's practice determining some convolutions. For the first example, we will find the convolution of f of t equals e to the t and g of t equals t for t greater than or equal to 0. So again, we have the convolution of f of t and g of t written in either of these two forms, which is equal to the integral from 0 to t of f of tau times g of the quantity t minus tau d tau, where f of tau is e to the tau and g of the quantity t minus tau is just t minus tau. And therefore the convolution of f of t and g of t equals the integral from 0 to t of e to the tau times the difference of t and tau d tau. To integrate, we need to perform integration by parts, which I've shown here in blue on the left, where u is equal to t minus tau and dv is equal to e to the tau d tau. We differentiate to find du, we integrate to find v, and apply the integration by parts formula. The result is the difference of t and tau times e to the tau plus integral of e to the tau d tau. Integrating e to the tau with respect to tau, the final result is the difference of t and tau times e to the tau plus e to the tau plus c. But of course, we have a definite integral, and therefore the antiderivative is just the difference of t and tau times e to the tau plus e to the tau, and now we find big F of t minus big F of 0. Recall in performing this substitution, we substitute t for tau and then 0 for tau because we integrated with respect to tau, not t. So here we have big F of t minus big F of 0. Simplifying, the convolution of f of t and g of t is equal to e to the t and then minus the sum of t and 1, giving us a final result of the convolution of f of t and g of t equals e to the t minus 1. Let's take a look at a second example. We're asked to find the convolution of f of t equals sine 2t and g of t equals cosine 2t for, again, t greater than or equal to 0. So again, we have our definition of the convolution of f of t and g of t. The result is the integral from 0 to t of sine 2 tau times cosine of 2 times the difference of t and tau d tau. For the next step, we will apply the trig identity shown here at the bottom of the screen, where cosine x times sine y equals 1/2 times the difference of sine of the quantity x plus y and sine of the quantity x minus y. Be careful when applying this identity because the cosine function in our integrand function is the second part, and the sine function is the first part. After applying the trig identity, the result is an integrand function of 1/2 times the difference of sine 2t and sine of the quantity 2t minus 4 tau. You may want to pause the video and verify this result. And now we find the antiderivative. The integral of 1/2 sine 2t with respect to tau is just 1/2 tau times sine 2t. We're treating 1/2 sine 2t as a constant because we're integrating with respect to tau. And then to integrate negative 1/2 sine 2t minus 4 tau, we need to perform u substitution, which I've shown here on the right, where u is equal to 2t minus 4 tau, du equals negative 4 d tau, and therefore negative 1/4 the u equals d tau. Notice we end up getting 1/2 times negative 1/4, which gives us minus 1/8 times cosine of the quantity 2t minus 4 tau. And now again we find big F of t minus big F of 0 by substituting t for tau and then substituting 0 for tau. So in this first set of parentheses we have big F of t, in the second set of parentheses we have big F of 0. And now we simplify. In the first set of parentheses we have 1/2 t sine 2t minus 1/8 cosine of negative 2t. And then the second set of parentheses we have minus negative 1/8 cosine 2t, giving us plus 1/8 cosine 2t. At this point we can still simplify. Recall the trig identity cosine negative x equals cosine x, and therefore negative 1/8 cosine negative 2t is equal to negative 1/8 cosine 2t. And then if we add 1/8 cosine 2t, these two terms simplify out or sum to 0, and therefore the final result is the convolution of f of t and g of t equals 1/2 t sine 2t. Now we will see how we use the convolution to determine an inverse Laplace transform. Let f of t and g of t be of exponential order, then the Laplace transform of the convolution of f of t and g of t, written in either of these two forms, is equal to the Laplace transform of the integral from 0 to t of f of tau times g of the quantity t minus tau d tau, which equals the Laplace transform of f of t times the Laplace transform of g of t. Notice on the right here we have the product of two Laplace transforms. In other words, the Laplace transform of a convolution, shown here on the left, is the product of the Laplace transforms, shown here on the right. The simplest way to use this result is in reverse. So if we start with the Laplace transform of the convolution of f of t and g of t equals the Laplace transform of f of t times the Laplace transform of g of t, we can write the right side as big F of s times big G of s. Then if we take the inverse Laplace transform of both sides of the equation, we have the convolution of f of t and g of t equals the inverse Laplace transform of the product of big F of s and big G of s. This theorem can help us determine inverse Laplace transforms and therefore help solve differential equations. So again, one more time, because the Laplace transform of f of t equals big F of s and the Laplace transform of g of t equals big G of s, we can say the product of big F of s and big G of s equals the Laplace transform of the convolution of f of t and g of t. And if we take the inverse Laplace transform of both sides of the equation, again we have the inverse Laplace transform of big F of s times big G of s equals the convolution of f of t and g of t. Let's take a look at how we will use this. Let's determine the inverse Laplace transform of 1 divided by the product of the quantity s plus 1 and s squared. Going to the next slide, let's first write this as a product of two functions of s, and therefore we have the inverse Laplace transform of 1 divided by the quantity s plus 1 times 1 divided by s squared. From here, if we find f of t and g of t, we can then find the convolution of f of t and g of t to determine the inverse Laplace transform. Well, the inverse Laplace transform of 1 divided by the quantity s plus 1, using the table here on the left, where a is equal to 1 gives us e to the negative t, and the inverse Laplace transform of 1 divided by s squared is equal to t. And therefore the inverse Laplace transform is equal to the convolution of e to the negative t and t. And we can write this convolution as the convolution of t and e to the negative t. And now we apply the definition of the convolution, which if needed is shown here at the bottom of the screen, where f of t is equal to t and g of t is equal to e to the negative t. And therefore the convolution is equal to the integral from 0 to t of tau times e to the power of the opposite of t minus tau d tau, which again requires integration by parts, where we let u equal tau and dv equal e to the power of the opposite of t minus tau d tau. We differentiate to find du, we integrate to find v, and apply the integration by parts formula, then integrate e to the power of the opposite of t minus tau d tau. The final result is tau times e to the power of the opposite of t minus tau minus e to the power of the opposite of t minus tau plus c. But of course we have a definite integral, and therefore we use the antiderivative tau times e to the power of the opposite of t minus tau minus e to the power of the opposite of t minus tau, and we have our limits of integration from 0 to t. And now we determine big F of t minus big F of 0, which will give us the inverse Laplace transform of 1 divided by the product of s plus 1 and s squared. So here we have big F of t, where we substituted t for tau, and then minus big F of 0, where we substituted 0 for tau. And now we simplify. Big F of t simplifies to just t minus 1. Notice both exponents on e are equal to 0, and e to the 0 is equal to 1. And then big F of 0 simplifies to e to the negative t because of this last term here. And therefore the inverse Laplace transform is e to the negative t plus t minus 1. In the next lesson, we'll get into more how we will use this to solve differential equations. I hope you found this helpful.